Hello everyone, I'm Saikat Gayen. I'm from IIT Varanasi. And so my talk is title is Recovering Redshifted 21 centimeter signal power spectrum, and the aspect is the systematics in high dynamic range interferometric observation. And here is my collaborators. So this is continuation of Prosun's talk, and as we see that in presence of calibration error, in presence of systematics, there is a bias and excess variance in 21 centimeter signal power spectrum when there is a strong foreground. And also this calibration error is depend on time and frequency of our observation. So the first part of my talk, I will discuss how the calibration error depend on the time correlation, and for that we will have observation of UGMRT band 3 observation of where this frequency separation is 0, and we have the single channel observation. And second part of my talk, I will discuss about calibration error depend on time and frequency both. For that we will discuss this SK1 low mock observation. And this observation by Chakraborty et al. This is UGMRT band 3 observation of LIS in one field of frequency range of 300 to 500, and this is like redshift of 2.5. And we use this foreground model, it's a diffuse galactic synchronous emission model of this power law foreground model. And here are some gain characteristics, like as we discussed in previous talk, that in our simple gain error model, we assume that all the residual gain are similar for all antenna, and they follow the Gaussian distribution. For that, we do a Komolov-Smirnov test of time series data of our residual gain error. And as we see that the K statistics value are more or less 0.1 and 0.2, that means that we have only 10% chance that it will not follow Gaussian distribution. And so we can simply say that most of the antenna residual gain error follow the Gaussian distribution. And also we here we see the gain error mean and standard deviation of residual gain error. And also we do some additional flagging looking at the standard deviation. And these antenna are standard deviation of more than 8%, the standard deviation of residual gain error. So we flag those antenna, we tagging those antenna are bad antenna, and we flag those antenna for our further calculation. And this is time correlation effect. And here this first, if we define this self structure normalization structure function to estimate the time correlation time. And as an example, we see a 16 antenna and imaginary part of LL polarization. Here we say how we can calculate the time correlation time, and then we check every possible time of every possible cross correlation between real imaginary part or LL RR polarization or different antenna cross correlation, and we find the correlation time that like for 70 to 80% case, this correlation time is less than our 2 times of integration time. So we can say that there is no time correlation between two antenna or two polarization or two real and imaginary part of residual gain error. And this is baseline pair fraction of this our UGMRT observation of a 6th May data, and it is discussed. And this is the time correlation effect chi for our observation and our interested baseline range. And this is our result. And here, this is this gray dot line. This is 21 centimeter signal power spectrum. And this is the uncertainty, thermal uncertainty when there is no residual gain error. But in presence of residual gain error, there is a bias and a excess variance. And as we see that for every baseline, our interested baseline range, this bias and excess variance is greater than the thermal uncertainty. And also, we have done one thing, that we do some additional flagging looking at the gain characteristics. And for by this additional flagging, flagging some bad antenna, we improve our uncertainty due to the residual gain error. This black dashed line is after flagging some antenna, we improve our uncertainty. And this is the detection significance. Here is the hours, like how much our time we have to we need to detect the 21 centimeter signal. And this is detection significance line. This horizontal line is the when the signal and noise are same, and this is 3 sigma detection line, and this is 5 sigma detection line. If we consider the angular multiple of L equal to 2000, And this black dashed line, this is when there is residual gain error presence and this gray dashed line when there is no residual gain error. So when there is no residual gain error, we can see that only on 200 hour of observation, we can detect 21 centimeter signal. But when there is presence residual gain error, there we need likely 2000 hours of time to detect our signal. But in higher baseline, when L equal to 6000, then most of the uncertainty is coming from the thermal part only. So in that case, no, there is no effect of residual gain error. So all right, now we go to the multi-angular frequency power spectrum, where we will discuss the time and frequency correlation to the calibration and dependency. And for that, we will do a mock observation of SK on low AA4 configuration. And this is of 1024 channel, indication time is 1 second. And this, I forget to mention that the sky model, we use the Sontes et al. Foreground model, and the 21 centimeter signal is from Mandal 2023 of redshift of Z equal to 8. And here is the baseline fair fraction of SK on low for our interested region of baseline. And as we can see that the dominant is the N1 and N3 type of baseline pair fraction is dominant all these region. And so this baseline pair fraction has effect to the bias and residual bias and excess variance. And now see this result. These are the bias, total uncertainty and thermal uncertainty in delta nu L plane. And this solid line, for every case, this solid line is the signal by bias, and the dashed line is the signal by uncertainty contour. And this contour means the and below this contour line, this region of L delta nu plane, where we can detect our signal. And as you can see that we need of 120 hours of observation to detect 21 centimeter signal when there is no residual gain. And this result is discussed also Mandal 223 paper. Now, when there is residual gain, we can see that there is no detection at 128 hours. When if we increase our observation time like to 1024 hours, then we can get 10 sigma detection of 21 centimeter signal. But if we increase our calibration accuracy, to here calibration accuracy was 1%. If we increase our calibration accuracy, then only in 128 hours we can detect our signal. We also check that if we increase our bandpass accuracy, like we decrease this bandpass correlation frequency, but in that case there is no significant change for detection of 21 centimeter signal. But if we check in case of bias only, we can say that for this bias we can get more detection for this 120 hours, more calibration accuracy, and less less bandpass error bandpass correlation. That means that bandpass has a frequency dependent effect that will I discuss later. Like if you see this plot, if you see here that Prasun discussed in previous talk, that in that figure you see that this is 1024 hours of observation, and in this region, if you see this is 10 sigma detection, you may thought that we can detect 21 centimeter signal here, but you can see that there is the bias only has 1 sigma detection. So what you measure actually is bias. But if we increase our calibration accuracy 5 times, in that case we can get this 21 centimeter signal detection. There we can say there is no bias and no uncertainty also. Now, this is important finding in our result, that this plot is from Asif 2023 paper, where what they have done, when our frequency delta nu frequency range, the 21 centimeter signal is actually decorrelated, but there is foreground. So if we model our foreground after this 1 megahertz frequency range, in this region there is only foreground, then extrapolate our foreground in that region and subtract that foreground, we can get only 21 centimeter signal region. But we can see that our this bandpass frequency dependent thing is decorrelated after the 21 centimeter signal. So what we thought that in this region it's free of all other things, there is only 21 signal, but there is bias things also, because bias is decorrelate after the 21 centimeter signal. So what we can do that, if this bandpass error, actually we can increase our bandpass accuracy, bandpass gain error is less. For that thing, the first, there is two term in bias. First term, the bias, the frequency dependence come from foreground maps. So we can mitigate that part by this method of ASIF. We can mitigate this first part of bias. But this part of bias, second part of bias, that is coming from the bandpass frequency correlation mainly. We have to think about this part. This actually contaminate our result. We have 21 center signal and this part of bias. So this is conclusion of my result, is that when there is no residual gain error, we need 120 hours of observation. But in presence of residual gain error, we have to increase our observation time. But if we increase our calibration accuracy, we can detect our signal in 128 hours. And also the thing is that there is a part of bias, that the second term of bias, that has a bandpass frequency correlation, and that we have to think about it, because it is decorrelated after the 21 center signal. So for get the bias free detection, we have to think about the second part of bias that depend on this bandpass correlation. Thank you.
Thanks, Saikat. Questions? Yeah, Ilian.
I have two questions, so very nice again. So one is that, I mean, I think early on you showed, right, that sort of your, the average of your gain residuals is consistent with 0, right? If I understood it correctly, you had a plot where you showed, okay, the mean is sort of 0, and then you have a standard deviation, right? Very early on in your talk, which I don't fully understand, because right, the mean of it usually you get from a calibration process when comparing some model to what you actually observe. So you sort of subtract, right, the out any errors, right? So your residuals by definition will on average be 0. So maybe I misunderstood this. I think you just, this one here, right? You say mean there on the right bottom, not the right bottom.
These things is mean. Basically, if there is no calibration error, then this mean should be 0. But we have some residual gain error. So for that, we have some percentage of residual gain error.
Yeah,
so
maybe I'm misunderstanding what you mean by mean. I would think, right, that the mean it's at the residual gains at the top. So I thought, okay, right, even if you're factor 2 off in the gain, right, you're making that correction of factor 2, and then your residuals have a mean of 0 by definition, right? But maybe I'm misunderstanding this.
Leo, it's just that you have subtracted 1 before plotting this.
Yeah.
Because you know that the gain will be 1 if everything is correct.
Yes or no, but we can talk about that, because even in the mean there can be an error when you do it like this. If
that's
you do it,
what you were seeing here.
Yeah. Okay. Yeah. And the other sort of question I have, again, right? You are sort of right. You're building up a mathematical model here of how the gains and the and how they correlate over time and frequency. But of course, right, there's a reality of what the gain can really do because of the amplifiers and the instrument, right? So it can be, right, physically very smooth, but you can still have these effects because you're making gain modeling errors. Now, right, many of us have solved that by, right, imposing constraints on the gains by either smoothing them or, right, fitting models to them that are very, very smooth, right? So that actually puts a much less stringent requirement on the calibration, because you're allowing for those fluctuations, but you're so effectively filtering them out, right? This is not what you're doing here, right? You are really trying to say, okay, what could be after that filtering still be allowed, let's say, before it goes horribly wrong?
Yeah, but see, once you are doing the filtering, even in bandpass that we do regularly, you will introduce the correlation just by doing the filtering. Now,
so it's those sort of residuals that
those
you're
will be here. So one idea that we are thinking of is that if you look at the SK, so that N4 type of baseline pairs, which are the dominating ones, if you just use them, then none of these will arise.
Right.
So that will be a, but right now, how to do that algorithmically is difficult
Mhm.
because you have to go through all the ones.
Yeah, yeah. Okay, very nice. Thanks.
Thank you, Prasun. Thank you. Thank you.
Any quick questions before we move to the next talk? If not, let's thank Saikat once again.